Hello everybody, welcome to our channel EASI, everything about semiconductor industry or everything that you need to know about semiconductor industry. Today we are going to talk about semiconductor packaging. So let's get started. In our previous videos we have talked about how silicon dies are fabricated and also have covered the semiconductor end products. Today, we will talk about packaging, which serves as the critical interface between the two. That is, the silicon die on one hand and the outside world on the other. The quality of packaging directly impacts overall device performance, reliability, and longevity. It fulfills three essential roles, namely mechanical protection against physical damage and environmental factors, electrical connection enabling signals to flow between the chip and the circuit board, and finally, thermal management dissipating heat generated during operation. So the question is, what is semiconductor packaging? Semiconductor packaging refers to the enclosure that houses and protects the semiconductor die, the tiny silicon chip containing the integrated circuit or the IC. This protective shell serves as the critical interface between the microscopic world of transistors and the macroscopic world of electronic systems. The package provides a stable mechanical structure that allows the fragile die to be handled, tested, and mounted onto circuit boards. The package facilitates electrical connections between the semiconductor die and the printed circuit board or the system, enabling signal transmission and power delivery through carefully designed interconnects. It also shields the delicate silicon die from environmental hazards including moisture, dust, and mechanical stress, ensuring long-term reliability and consistent performance. There are broadly four types of packaging. First is a through-hole package. It is a traditional type of packaging that includes DIP or the dual inline package, or SIP, the single inline package. It offers robust mechanical connections for reliable assembly. Next comes the surface mount packaging. These compact designs include quad flat package or the ball and grid array packaging that enables automated assembly and higher component density on PCBs. Third are the advanced packages. Cutting-edge solutions like the chip scale package or the package on package or the 3D IC stacking comes under this category, which provides maximum miniaturization and better performance. Lastly are the system in package or known as SIP. Integration of multiple dies and components within a single package is what is called a system in package. It combines diverse functions to reduce size and improve system level performance. Let's talk about each of these types of packaging one by one. So first, let's cover the through-hole and surface mount packaging. Through-hole packaging, like the dual inline package, offers robust mechanical mounting and easy manual soldering. It is ideal for prototyping and high reliability applications. On the other hand, surface mount packaging, like the quad flat packages, enable compact designs with automated assembly, higher component density, and improved high frequency performance for modern electronics. Next is the ball grid array. Ball grid array packaging is one of the popular ones, which uses an array of solder balls on the underside of the package for electrical connections. This design enables higher pin counts in a smaller footprint while delivering superior thermal and electrical performance. BGA or the ball grid array packages are ideal for high performance applications that requires reliable but dense interconnections. Now, let's touch upon some of the advanced packaging technologies. Advanced packaging technologies like 3D IC and the system in package represent the cutting edge of semiconductor integration. These solutions stack multiple dies vertically or combine heterogeneous components within a single package that enables dramatic improvements in performance and density. Key benefits include reduced interconnect lengths, lower power consumption, and significant miniaturization for next generation devices. The key components or the materials used in packaging are substrates. These are the foundation layer that supports and connects the die. Options include organic for cost efficiency, ceramic for high reliability, and silicon for advanced applications. Next are the encapsulants, like the epoxy molds that protect the die from moisture, dust, and mechanical damage while providing structural integrity and electrical insulation. Next are the solder and the interconnects. These are the lead-free solder alloys and copper pillars that create reliable electrical connections between the die and the substrate, enabling high-density I/O configurations. Lastly are the thermal interface materials. These specialized compounds that efficiently transfer heat from the die to heat spreaders or the sinks are very critical for managing thermal performance in a high power device. Now, let us talk about some of the key process steps of packaging. First is the die attachment. The semiconductor die is precisely mounted onto the substrate or the frame using adhesive materials. This establishes the foundation for all subsequent packaging steps. Next is the wire and the flip chip bonding. Electrical connections are formed between the die and the package using fine gold or copper wires, or through flip chip solder bumps for high density applications. Then encapsulation or molding has to be done. Epoxy molding compounds are applied to protect the die and the wire bonds from environmental damage, moisture, and mechanical stress. Lastly, the final packages undergo electrical testing and inspection before individual units are sent out for distribution. As semiconductor devices continue to shrink while asking for more and more performance demands, packaging industry face complex trade-offs like miniaturization versus heat dissipation. Smaller packages concentrate heat at a tighter space, making thermal management increasingly difficult as die sizes shrink and power densities rise. Signal integrity and crosstalk. Higher frequencies and denser interconnects increase electromagnetic interference, requiring careful design to maintain signal quality and reducing noise coupling. Mechanical stress and reliability. Thermal cycling mismatches between materials cause warpage and fatigue failures, demanding robust designs for long-term reliability. Thus, in order to mitigate all of these problem statements, it requires innovative solutions. Advanced thermal interface materials, novel interconnect architectures, and improved simulation is what is needed in order to face this challenge effectively. Now let's talk about some of those innovations or the emerging trends. One of them is called the fan-out wafer-level packaging. Fan-out wafer-level packaging enables thinner profiles and higher I/O density by redistributing the connections beyond the die edge. Thus, it is ideal for mobile and wearable devices. The next one is called the heterogeneous integration. This combines different die types and technologies in a single package that enables optimized performance and functionality for complex applications. And finally, we can utilize AI-driven automation and eco-friendly materials that can reduce environmental impact and also help to accelerate the design and manufacturing, and therefore improves the entire packaging life cycle. By now, we have established that packaging is an emerging technology that continues to demonstrate robust growth driven by increasing demand for advanced electronics, IoT devices, and automotive applications. With a compound annual growth rate of approximately 7%, the industry is projected to reach significant milestones over the next 5 years, reshaping how chips are integrated into modern systems. As semiconductor devices continue to shrink while demanding greater and greater performance, packaging technology must evolve to meet these challenges. The industry is moving towards system level packaging that provides solutions that integrate multiple functions into a single package. Heterogeneous integration and chiplet architectures come under that category, which enable unprecedented performance, however, providing very high density and flexibility. Future packaging will also prioritize eco-friendly materials and processes while advancing thermal and electrical optimization. Cost efficiency and environmental responsibility both will drive material innovation. To summarize today's session, the key takeaways are: semiconductor packaging is fundamental to modern electronics. It serves as the critical bridge between silicon innovation and the real-world applications. From traditional through-hole packages to the cutting-edge 3D IC integration, the industry continues to evolve rapidly. As devices become smaller and more powerful, packaging technology remains at the forefront of enabling next-generation performance and reliability. With that, we have come to an end to our today's session. Hope you liked it. Please like, share, and subscribe. And if there's a particular semiconductor topic that you want us to cover, please mention in the comment section below. Meet you in the next exciting session of EASI. Till then, stay safe and stay healthy.